Hello everyone, welcome to my session on serverless in Azure as part of Azure Advent Calendar. First of all, I would like to thank Gregor and Richard to get me a slot at the last minute. I have loved this idea where people from different parts of the world have come together to share their knowledge with the community. I can only say that community rocks and it's great to be part of Azure family. Alright, let's get started. Few things about me. I have over 13 years of experience working across Microsoft technologies, designing and developing enterprise-class distributed systems. I am a Microsoft certified Azure Solutions Architect. I am currently working for Kivit as a cloud architect, and I am based out of Omaha, Nebraska, which is in Midwest US. I am a regular speaker at local .NET user group, often speaking on Azure-related topics, and I also own a blog, vaibhavgujral.com. I am a co-organizer of Omaha Azure user group as well. You can contact me via my blog, my Twitter handle, or my email. Let's jump onto the agenda. We are going to touch upon the following sections today. We will see what is serverless, what are the different serverless offerings in Azure, what are Azure Functions and Logic Apps. We will go through some of the concepts of Azure Functions and Logic Apps as well. Serverless has been a hype word in last few years. It is one of the coolest things that I have come across after cloud computing became mainstream. Serverless is a misleading term. Literally, serverless translates into something which has no servers, which is not true. Serverless workloads run on servers only. So it is misleading to say that there are no servers. Instead, think of it as less server. Serverless architectures essentially removes the need for server management. Servers, infrastructure, and operating systems are provisioned on demand for execution time and decommissioned when execution is done. It is important to understand the benefits we get out of serverless architectures. Most of us would have come across situations where we would have deployed our resources on a hosting platform and we would be keeping a server component always up and running so that whenever the actual request comes in, the server responds back. That approach came with a cost. Just to handle requests at a specific time, we used to maintain servers up and running 24/7. In serverless, as the cloud provider provisions the resources on the fly whenever the code is executed and deprovisions the resources thereafter, it essentially removes the need for server management and retaining always-on server components. Likewise, not only the resources are provisioned and deprovisioned on the fly, resources are also auto-scaled depending upon the requests and events. Best part is that the cloud provider charges only for the time during which the resources were provisioned, which essentially translates to the time the code is executed. The result is immense cost savings in both operational and saving costs. Couple of use cases for serverless are also coined as function as a service and integration platform as a service. Under FaaS, independent code pieces are executed as functions. Some examples include Azure Functions, AWS Lambda, and Google Cloud Functions. Integration platform as a service refers to building and deploying integrations and business processes within the cloud and between the cloud and the enterprise. One of the example is Azure Logic Apps. If anyone has experience in BizTalk, they will understand what I am talking about. Think of BizTalk as a service. Coming to serverless offerings in Azure, Microsoft has been adding serverless features to many services ranging from Kubernetes, SQL databases, Azure Functions, Logic App-based workflows, Visual Studio Online, and API gateways. We are going to talk about functions and Logic Apps today. Let's talk about Azure Functions first. Azure Function is a serverless compute service offered by Azure that can run code on demand. I call these small pieces of code as functions. Just think that if you can write the code you need for the problem at hand without worrying about the whole application or the infrastructure to run it, Most importantly, you can deploy that piece of code independently and execute it on demand. Sounds interesting, right? It is easy too. Azure Functions provide out-of-the-box templates for some of the most common scenarios that we come across daily as a developer, ranging from connecting to storage, image processing, exposing REST APIs, Internet of Things, running a script or code in response to an event, and so on. Azure Function comes in pretty handy in these scenarios. Further, you can share these functions across your applications and developers' productivity gets a boost. Lastly, I assume if you would have worked on Azure Web Apps, you would have also worked on web jobs, which allowed us to write background tasks in the same context as a web app. Think of Azure Functions as a serverless extension of Azure Web Jobs. In fact, Azure Functions SDK utilizes Azure Web Jobs SDK. Microsoft offers a choice of language in which we can write our code for Azure Functions. Azure Functions supports C#, F#, JavaScript, Java, PowerShell, Python, and TypeScript. Since it's serverless and Azure Compute resources are provisioned only for the time when the code is executed, we pay only for the time the code is executed, as the resources are deprovisioned after that. Functions support NuGet and NPM, so we can bring in our own dependencies and use them in our code pretty much as we will do in any of our other projects. We will talk later about what is a HTTP trigger, but for now, just make a note that functions can also be triggered by HTTP requests, and Azure Functions supports OAuth providers such as Azure Active Directory, Facebook, and Google, etc. for authentication. Since Azure Functions are part of Azure ecosystem, they offer seamless integration with many of the Azure services. There are different ways to develop and deploy Azure Functions, but it makes development quite flexible. As a developer, I can work on one function using C#, and my co-developer who loves JavaScript can work on another function using JavaScript, and we can utilize both these functions in single architecture. Makes sense? Recently, Microsoft has announced support for PowerShell, which opens up the avenues for administrators to run their PowerShell runbooks as Azure Functions. Isn't it amazing? Lastly, Azure Functions Runtime is open source and is available on GitHub. If you are interested, you might go ahead and check it out. The Azure Functions Runtime provides a way to take advantage of the simplicity and flexibility of the Azure Functions programming model on premises. Built on the same open source roots as Azure Functions, Azure Functions Runtime is deployed on premises to provide a nearly identical development experience as the cloud service. The Azure Functions Runtime has two components: Azure Functions Runtime Management Role and Azure Functions Runtime Worker Role. The management role provides a host for the management of Azure Function on premises. This role is responsible for hosting of the Azure Function Management Portal, distributing functions across multiple function workers, and providing a publishing endpoint so that we can publish our functions directly from Microsoft Visual Studio by downloading and importing the publishing profile. The worker role are actually deployed in Windows containers and are where the function code executes. There are three major versions of the Azure Functions Runtime: 1.x, 2.x, and 3.x. Version 1.x is based on .NET Framework 4.6, whereas version 2.x and 3.x are based on .NET Core versions 2.2 and 3.1 respectively. All the versions are supported for production scenarios. The point to note here is that version 1.x is currently in maintenance mode and no active developments are taking place in this version. Enhancements are provided only on versions 2.x and 3.x. Here you can see the language support for all the versions of runtime. In all the versions, C#, F#, and JavaScript are GA, whereas 2.x and 3.x supports richer set of languages including Java, PowerShell, Python, and TypeScript. For understanding more differences in each of these runtime versions, check out Microsoft Azure documentation online. Since function is part of Azure ecosystem, they can be integrated easily with many Azure services and also some third-party services. Any of these services can either trigger a function execution or they can serve as an input or output for your code. Following services can be integrated with Azure Functions, Azure Cosmos DB, Event Hub, Event Grid, Notification Hub, Service Bus queues and topics, Storage Blob queues and tables. Azure Functions can connect to on-premise systems using Service Bus. Azure Functions can also connect with Twilio for SMS messaging. One of the Merriam-Webster's definitions says, a trigger is something that acts like a mechanical trigger in initiating a process or reaction. This defines pretty much what an Azure function trigger does. It essentially defines how a function is invoked. Triggers are out-of-the-box templates to trigger execution of an Azure function. A function can have exactly one trigger. A trigger can have an associated data, which is usually the payload that triggered the function. Azure Functions supports the following triggers, ranging from HTTP trigger, where the execution of the code can be triggered by using an HTTP request, timer trigger, where the code can run on a predefined schedule, Cosmos DB trigger, where you can process your Azure Cosmos DB documents when they are added or updated in collections. Blob trigger, where you can process your Azure Storage blobs when they are added to the containers. Queue triggers can also be used to respond to messages when they are written in the Azure Storage queue. Event Grid trigger and Event Hub trigger can be used to respond to events delivered to a subscription or within a Azure Event Grid or to an Azure Event Hub. Service Bus Queue trigger and Service Bus Topic trigger can be useful for connecting your code to other Azure services or on-premise services by listening to message queues or by subscribing to topics. Input and output bindings provide a declarative way to connect to data from within your code. Bindings are optional and a function can have multiple input and output bindings. Triggers and bindings let you avoid hard-coding the details of the services that you are working with. Your function receives data, for example, the content of a queue message in function parameters. You can send back data to create another queue message by using the return value of the function. As I said, there could be two types of bindings, input and output. A function can have multiple input and output bindings. Input and output bindings use in and out binding directions. Some binding supports special binding direction in-out, indicating they support both in and out directions. For Runtime version 2.x, binding extensions are provided in NuGet packages, and to register an extension, package needs to be installed. The same applies for the version 3.x. When you develop Azure Functions by using the Azure portal, triggers and bindings are configured in a function.json file. The portal provides a UI for this configuration, but you can edit the file directly by changing to the advanced editor. When you develop functions by using Visual Studio to create a class library, you configure triggers and bindings by decorating methods and parameters with attributes. Suppose you want to write a new row to Azure Table Storage whenever a new message appears in Azure Queue Storage. This scenario can be implemented using an Azure Queue Storage trigger and an Azure Table Storage Output binding. Here is a function.json file for this scenario. The first element in the bindings array is the queue storage trigger. The type and direction properties identify the trigger. The name property identifies the function parameter that receives the queue message content. The name of the queue to monitor is in the queue name, and the connection string is in the app setting identified by connection. The second element in the bindings array is the Azure Table Storage Output binding. The type and direction properties identify the binding. The name property specifies how the function provides the new table row, in this case by using the function return value. The name of the table is in the table name, and the connection string is in the app setting identified by connection. In a class library, the same trigger and binding information, queue and table names, storage accounts, function parameters for input and output, is provided by the attributes instead of a function.json file. One of the most powerful features of triggers and bindings is binding expressions. In the functions.json file and in function parameters in code, you can use expressions that resolve to values from various sources. Most expressions are identified by wrapping them in curly braces. Binding expressions using app settings are different from other types because those are wrapped in percentage signs. Some of the common types are app settings, file names, trigger metadata, JSON payloads, new GUIDs. Alright, let's get started with Azure Function tooling with Visual Studio. On this screen you are seeing a snapshot of installation wizard for Visual Studio 2019. During installation of Visual Studio 2019, you can select the checkbox for Azure Development, which includes the Azure SDK and the requisite tools and project templates for building cloud apps. Once this is installed, you can start developing your Azure Functions using Visual Studio 2019. Once Visual Studio 2019 is set up, open Visual Studio and click on New Project. Select Azure Functions template and click Next. In the older versions of Visual Studio, you might need to go to Extensions under Tools and install Azure Functions and Web Job Tools. On the next tab, give a name to your function, provide the location to keep the source code, and click Create. In the next tab, you need to choose the trigger type for your Azure function and click Create. For the benefit of the people who use Visual Studio Code, you need to install the Azure Functions extension for Visual Studio Code. You also need to install Azure Functions core tools to develop and test your functions on your local computers from the command prompt or terminal. Your local functions can connect to live Azure services, and you can debug your functions on your local computer using the full functions runtime. You can even deploy a function app to your Azure subscription using Azure Functions core tools. There are 3 different versions of Azure Function core tools: version 1.x, version 2.x, and version 3.x. Version 1.x is supported only on Windows, whereas version 2.x and 3.x are based on .NET Core, and they support Windows, Mac OS, and Linux. They also need Node.js, including NPM. Coming to pricing, for Azure Function, there are 3 different pricing plans. To start with, the first plan is consumption plan, where you pay for the time the code is executed. When you create an Azure function, this is the default hosting plan. The second option is premium plan, which is similar to consumption plan but with some added features, including perpetually warm instances to avoid any cold start and VNet connectivity. The third option is dedicated plan, which is same as app service plan for a web app, where you get dedicated resources for your Azure function. Do remember to enable always on when you create your Azure function under a dedicated plan. to avoid any cold start. Let's talk more about consumption plan. As I was saying earlier, under consumption plan, you pay for the time that your code runs. Under consumption plan, Azure automatically allocates compute power when the code is running. It adds or removes function hosts instances based on the number of events that its functions are triggered on. Each instance of function host is limited to 1.5 gigabytes of memory. All functions within the same function host share the same resources and are scaled together. Function code files are stored on Azure File Shares, which is backed by Azure Blob Storage. The point to note here is that Azure Functions under consumption plan do timeout after configurable period of time using function timeout property. By default, the property is set to 5 minutes and the maximum can be 10 minutes. Jumping on to premium plan, which is similar to consumption plan except it comes with some added features. The common problem with consumption plan is that since the resources are commissioned and decommissioned only during the time the code is executed, which sometimes result into cold start for the function when it is called the very first time. Premium plan takes care of that issue by perpetually providing warm instances to avoid any cold start. Under premium plan, Azure Functions can also connect to virtual networks. They support unlimited execution duration. With premium plan, you also get access to premium instance sizes, including 1 core, 2 core, and 4 core instances. Under premium plan, it gives you more predictable pricing. For plans with multiple function apps, it also supports high density application allocation. Scaling under consumption plan. Azure Function uses a component called the scale controller to monitor the rate of events and determine whether to scale out or scale in. The scale controller uses heuristics for each trigger type. For example, when you are using an Azure queue storage trigger, it scales based on the queue length and the age of the oldest queue message. The unit of scale is the function app. When the function app is scaled out, additional resources are allocated to run multiple instances of the Azure Functions host. Conversely, as compute demand is reduced, the scale controller removes function host instances. The number of instances is eventually scaled down to 0 when no functions are running within a function app. Scaling can vary on a number of factors and scale differently based on the trigger and the language selected. However, there are few aspects of scaling that exist in the system today. A single function app only scales up to maximum of 100 instances. A single instance may process more than one message or request at a time though. So there isn't a set limit of number of concurrent executions. New instances will only be allocated at most once every 10 seconds. So in this diagram, you see how scale controller monitors the different events coming through different triggers, and based on that, it goes ahead and creates different function host instances to process each of those events. App service plan is same as an app service plan in a web app or an app service. It's also called dedicated plan for Azure Functions. Under this plan, you get dedicated resources based on the chosen tier like a basic or standard. The advantage of an app service plan is it's fixed costs because you get dedicated resources which are always up and running. Manual scaling and auto scaling are supported under app service plan just like it is supported in web apps. Under dedicated plans, you can run function apps just like web apps. Using a dedicated plan is very useful when app service plan already exists for a web app and function app can run at no additional cost. One important consideration for using app service plan is that The function app goes idle after a few minutes of inactivity. So in such cases, you should always enable always on to keep the functions running continuously and correctly. Under consumption plan, function apps are activated automatically. When we are developing Azure Functions, there is also a mechanism for logging based on Azure storage. It's useful for non-production environments with light workloads, and it can be disabled by deleting Azure Web Jobs Dashboard app setting. Azure Functions also comes with built-in support for application insights, which is the recommended way for logging Azure Functions for production workloads. If this is enabled, built-in logging on Azure Storage should be disabled. Telemetry data can be further queried using Application Insights Analytics, and telemetry might include traces, requests, exceptions, custom metrics, custom events, and performance counters. And this data is also queryable under Azure Monitor using Custo query language. Moving on to continuous deployment for Azure Functions, please note that it can directly be deployed through any source control of your choice, ranging from Azure DevOps to Jenkins and other. Deployments are configured per function basis, which means we can deploy all the functions within a function app altogether. If continuous deployment is enabled, please note that the access to function code in the portal is set to read only, and you cannot edit that function code in the portal. Azure DevOps, previously called as Visual Studio Team Systems, offers full support for Azure Functions. There are other ways to deploy Azure Functions, including zip deployment, ARM template deployment, and through deployment packages. Before jumping onto the demo, let's go through some of the best practices that are recommended when we are developing Azure Functions. Large long-running functions can cause unexpected timeouts. Whenever possible, refactor large functions into smaller function sets that work together and return responses fast. Functions should be stateless and idempotent if possible. Associate any required state information with your data. Idempotent functions are especially recommended with timer triggers. For example, if you have something that absolutely must run once a day, write it so it can run anytime during the day with the same results. Reuse external connections whenever possible. Don't mix test and production data in the same function app. Use async code but avoid blocking calls. Receive messages in batch whenever possible. Write defensive functions with the assumption that your function could encounter an exception at any time. Design your functions with the ability to continue from a previous fail point during the next execution. Let's jump onto a quick demo for Azure Functions. The first thing I'm going to show is how to create an Azure function in Azure Portal. To get started, I have already created a resource group under my subscription for the purpose of this demo. Under that resource group, I'm going to create an Azure function through the portal. Let's get started. I'll go and click on Add under the resource group and look for function app. I choose the function app and click on Create. It automatically chooses my subscription and my resource group. I'll go ahead and give a name to my function. Since it's not a containerized app, I leave the publish option for Docker container as is, but please note that there is an option to deploy your containerized apps as part of Azure Functions. I can choose any of the available runtime stacks here. Since I'm a .NET developer, I'm gonna choose .NET Core. I'll leave the default option under a region as Central US. You can choose any region that makes sense for your purpose. I'll go to the next tab for hosting. You will notice here that it gives an option to choose the plan type, which we have discussed in one of the slides before. It lists all the 3 plans here, ranging from consumption, premium to app service plan. I will stick with consumption plan for now, for the purpose of this demo. You will also note that it asks for creation of a storage account to host the function files. I'm gonna stick with Windows operating system, but you can also choose Linux here. I'll move on to next tab for monitoring, and by default it creates an App Insights instance for logging telemetry for my Azure function. I will leave that setting as is. I'll move to next tab. I don't need to provide any tags, but you should provide tags if you want to charge back your departments and teams for the Azure resources. I'll go to next review and create, and I'll go ahead and click create. It's gonna take a couple of minutes. I will be back once the deployment is ready. Looks like the deployment is ready and our function is created. I'll go to the resource. This is the Azure function which we just created through Azure portal. In fact, it's just an Azure function app. I'll go ahead and create a new function within it. It gives us an option to choose any editor of our choice, or we can create a function within the portal. I will go and choose in portal and click continue. I'm going to create a function with a webhook, as well as later I will show you how to create a timer trigger function as well. Let's go with webhook based function first. Here you go. What it has done is it has created a function with a default name for my HTTP trigger function. With a sample code, what it does is it looks for each request and see if there is a query parameter called as name. If yes, it prints a message called hello name. Otherwise, it asks the user to pass a query string in the request body. One thing you will notice here is the extension of this file, CSX. It stands for C# script file. I'll go ahead and run this function. So this is a test run that I have done for my function. I have passed the name Azure and it returns back with hello Azure with the status 200 OK. I'm going to fetch the function URL from here, and I'm going to do the same thing from Postman. I'll pass the name as Postman here, and I get the response hello Postman. I will go ahead and create another function here with a timer trigger. Notice here that when I go here and create my function within the function app, it gives me all the different options for using any trigger that I want, ranging from queue storage trigger to service bus queue and topic trigger, and all the topics that we have talked about in the slide deck. For the demo purpose, I'll choose a timer trigger. You will see here it needs a cron expression of the format for the time or the schedule at which this new function should run. What this denotes is that this function will run every 5 minutes. For the demo purpose, I'm going to change it to 1 so that it runs every 1 minute. I'll go ahead and click create, and it creates a timer trigger here. It generates the same C# script file for me with a sample code. In this sample code, what it is doing is just logging a single statement. I'm going to run this, and it will pop up the terminal, and my function has been executed once. If we'll wait here, it will keep on executing this for every 1 minute. Alright, that's pretty much concludes the demo for the Azure portal. Let's jump onto Visual Studio 2019, how we can do the same things in Visual Studio 2019. To start with Visual Studio 2019, go to File menu and create a new project. Scroll down and find the template for Azure function. Click Next. Choose the name and the location of your source code. Click Create. Choose the trigger that you want to create. I'll choose timer trigger here for now, and I will change the schedule to 1 minute. For the storage account, since I am running it locally, it gives me an option to either use storage emulator, which emulates the Azure storage account so that I can test it locally, or I can go ahead and I can browse and choose a storage account under my subscription. I'm going to stick with the storage emulator for this demo. I go ahead and create the function. It will take few seconds to create the function app. So it creates a function.cs class file for me with the same sample code that we have seen in the portal earlier. You will notice here that there are two different files here, host.json and local.settings.json. The host.json file contains global configuration options that affect all the functions under a single function app, whereas the local.settings.json file stores app settings, connection settings, and settings that are used by the local development tools, and these settings are used only when you are running your projects locally. Jumping back to function1.cs, I'll go ahead and quickly run this function app. It will build my solution and it will start the Azure Storage Emulator. You need to have Azure SDK installed as part of Visual Studio 2019 to enable and run the storage emulator. So here is my Azure function running. It has already been executed once, and it will come back again after 1 minute. It would have executed the next time. Let's jump onto Visual Studio Code to demonstrate an Azure function creation under Visual Studio Code. I'm inside Visual Studio Code now. I'll go ahead and go to the command palette. I will choose an Azure function create new project command, which comes as part of Azure Function Code Tools. I will choose the directory where I want to create all the files. I'll choose the language of my choice in which I want to develop my Azure function. I'll choose the available templates for the triggering. For this case, I will choose timer trigger. I'll go with the default function name and press enter. I'll retain the same function name. I'll make it 1 minute and press enter. I'll use the local emulator. It creates the same set of files here with the host.json, local.settings.json, and my timer trigger C#, which has exactly the same sample code I have shown you before in the portal and in Visual Studio 2019. I will go ahead and execute this function. It's running my function host, and here is my piece of code that was executed. It's executed here as well. It's going to wait for another minute and execute it later again. I'm going to go ahead and disconnect this. That concludes the demo for Azure Function. Let's keep things going. Before we jump onto the logic apps, I wanted to touch upon durable functions. Durable functions are an extension of Azure Functions that lets you write stateful functions in a serverless environment. It simplifies complex stateful coordination problems in serverless applications and provides stateful orchestration of function execution. It is built on top of Durable Task Framework, which is an open source framework in GitHub, but as a serverless evolution. Some typical application patterns supported by durable functions include function chaining, fan-out, fan-in, async HTTP APIs, monitoring, and human interaction. Under function chaining, the pattern of executing a sequence of functions in a particular order. Often the output of one function needs to be applied to the input of another function. Fan-out, fan-in refers to the pattern of executing multiple functions in parallel and then waiting for all to finish. Often some aggregation work is done on results returned from the functions. Under async HTTP APIs, we have the long-running action triggered by an HTTP call and then redirect the client to a status endpoint that they can poll to learn when the operation completes. Many processes involve some kind of human interaction. The tricky thing about involving humans in an automated process is that people are not always as highly available and responsive as cloud services. Automated processes must allow for this, and they often do so by using timeouts. By using human interaction pattern for durable functions, we can handle that problem. With Azure Function proxies, you should note that you can use these proxies to break a large API into multiple function apps, as in a microservices architecture, while still presenting a single API surface for clients. It defines an endpoint that serves as a reverse proxy to another API. We will jump onto Azure Logic Apps now. Azure Logic Apps are integration platform as a service offering under Azure. Using Logic Apps, you can schedule, automate, and orchestrate tasks, business processes, and workflows. Using Logic Apps, you can design and build scalable solutions for application integration, data integration, system integration, enterprise application integration, and business-to-business communication. Logic Apps comes with many ready-to-use built-in and custom connectors, which make them super easy to use. Some of the benefits that we get out of Logic Apps include visually build workflows with easy-to-use tools since it's all GUI based. It has first-class support for enterprise integration and B2B scenarios. Write once, reuse often. We can reuse our existing Logic Apps in multiple scenarios. Built-in extensibility through different. Finally, since it is serverless, you pay only for what you use. Just like Azure Function, a trigger is the first step in any Logic app, usually specifying the event that fires the trigger and starts running your Logic app. Actions are the steps that follow the trigger and perform tasks in your Logic app's workflow. After a trigger fires, Azure Logic Apps creates an instance of your Logic app and starts running the action in your Logic app's workflow. There are three kinds of trigger. Recurrence trigger. This trigger runs on a specific schedule and is not tightly associated with a particular service or system. Polling trigger. This trigger regularly polls a specific service or system based on the specific schedule, checking for new data or whether a specific event happened. If the new data is available or the specific event happened, the trigger creates and runs a new instance of your Logic app, which can now use the data that is passed as input. Push trigger. This trigger waits and listens for new data or for an event to happen. When new data is available or when the event happens, the trigger creates and runs new instances of your Logic app, which can now use the data that is passed as input. Every time a Logic app definition runs, the triggers, action, and connector executions are metered, and that is how Logic apps are priced. Jumping to built-in connectors, some of the most common connectors that you might use as triggers include schedule to run your logic app on a specific schedule, HTTP to communicate with any endpoint over HTTP with both triggers and actions for HTTP, HTTP plus Swagger, and HTTP plus webhook. Request to make your logic app callable from other apps or services. Batch, process messages in batches with the batch messages trigger. Azure Functions trigger can be used to call Azure Functions that run custom code snippets from your logic apps. Call triggers and actions defined by your own APIs that you manage and publish with Azure API Management trigger. Call Azure API apps or web apps hosted on Azure App Service using Azure App Service trigger. Likewise, you can call other logic apps through Azure Logic App trigger. There are few control workflow connectors like condition, which can be used to evaluate a condition and run different actions based on whether the condition is true or false. You can perform the same actions on every item in an array in each iteration using for each. Group actions into scopes, which gets their own status after the action in the scope finishes running. Group actions into cases, which are assigned unique values except for the default case. Run only that case whose assigned value matches the result from an expression, object, or token. If no matches exist, run the default case. For this, use this switch workflow. Terminate, stop an actively running logic app workflow. Using until, you can repeat actions until the specified condition is true or some state has changed. Logic Apps provides built-in actions for working with data outputs and their formats. For example, data operations to perform operations with data like compose, creating CSV and HTML table files, parsing JSON, and so on. Datetime to perform operations with timestamp like converting time zone, getting current time, getting past time, getting future time, and so on. Variables, you can perform operations with variables like appending to array variable, appending to string variable, incrementing or decrementing variables, initializing variables, or setting a value for a variable. Logic Apps provide some of the popular standard connectors for automating tasks, processes, and workflows with most of the common systems and services. For example, Azure Service Bus, SQL Server, Office 365, Azure Blob Storage, SFTP, Dynamic 365, Salesforce, Twitter, Event Hub, and Event Grid. Here are some commonly used standard connectors that Logic App provides for accessing data and resources in on-premises systems. Before you can create a connection to an on-premises system, you must first download, install, and set up an on-premises data gateway. This gateway provides a secure communication channel without having to set up the necessary network infrastructure. Logic Apps provide standard connectors for building B2B solutions with your Logic Apps when you create and pay for an integration account, which is available through the Enterprise Integration Pack in Azure. With this account, you can create and store B2B artifacts such as trading partners, agreements, maps, schemas, certificates, and so on. To use these artifacts, associate your Logic Apps with your integration account. If you currently use bespoke servers, these connectors might seem familiar already. Logic Apps provides these enterprise connectors for accessing enterprise systems such as SAP, IBM MQ, and so on. Alright, let's jump onto a demo for Logic App. I'll go ahead and jump back to the Azure portal again. I'll go back to my resource group and click Add. I will go and search for logic app. I'll click create. I'll give a name here. I'll choose the subscription. I will use an existing resource group here, which was the one under which I have created the Azure function. I have an option to choose a log analytics workspace to store the telemetry through my logic app. I have not created a log analytics workspace upfront, so I will keep that option off, but you can go ahead and switch it to on and map it to a log analytics workspace if you want to store telemetry from your logic app and query it under your Azure Monitor instance. I will click create here. It will take hardly a minute to create the logic app. Alright, the deployment is ready. I will go to the resource. The very first time when I jump onto the logic app tab or the blade, it gives me an option to create a logic app under the logic app designer. I can choose any of the available connectors here as trigger and actions and define my own workflow. I'll start with a recurrence trigger. I want my logic app to run every 1 minute. And I want to call the function app that I created through in Portal for my STTP trigger a moment back. I'll choose STTP. I'll use STTP action. I'll choose the method, which is post. I'll provide my function URL here. I'll pass my body. Here, I will change it to logic app. And I leave the authentication as none. I'll go ahead and save the logic app. Once done, I'll go ahead and I'll run the trigger. It just got executed here. I'll click on here. It says that both of my trigger and actions were executed successfully. If there is any failure, it will give a red sign here. I'll open my action to see what was the response I got. And here was the response that was written from my function, hello logic app. Couple of things you should note here is you can go ahead and design your logic app using the logic app designer here. But what eventually it translates it into is an ARM template, which is defined here. We can use the same template to deploy our logic apps through Visual Studio 2019 or Visual Studio Code. That concludes my demo for the logic app. This completes my presentation as well. I hope you will find this useful. Thank you so much for watching. Goodbye.